Living in a country where over 96% of the land is desert, Egypt's 95 million people have been virtually trapped along the Nile for thousands of years. But now they're breaking free from that limit by doing something no modern nation has ever done, building a massive man-made river straight through the desert. Tens of millions of liters of water are pumped from the Nile, pushed through giant pumping stations, and flow through concrete canals so wide they look like real rivers, all to cross burning deserts over 45 pounds and bring life to land that has never been farmed before. But how exactly was this new Delta River planned, built, and operated in one of the harshest environments on Earth? Let's find out with Mandarin Tech. When people think of Egypt, they usually picture the pyramids, grand monuments of the ancient world. But few realize the harsh reality this nation of over 110 million people faces today. Nearly the entire population is packed into a narrow strip of land along the Nile River, which makes up less than 5% of the country's total area. The rest, it's almost entirely covered by the vast Sahara Desert. As the population keeps growing, arable land becomes dangerously scarce. Egypt is confronted with a life or death question. How can they bring the life-giving waters of the Nile across the desert to create new spaces for living and farming? In the year 2021, the Egyptian government launched an unprecedented answer, the New Delta Project, a massive development plan with a total investment of more than 10 billion United States dollars. The project includes building hundreds of kilometers of artificial canals and water infrastructure, featuring the giant El Hammam pumping station, a main canal stretching over 170 kilometers across the desert, as well as secondary distribution channels, underground pipelines, reservoirs, and a smart water management system equipped with sensors and satellite monitoring. But the goal is not just to bring water for farming. Egypt aims to create an entirely new delta, redistribute its population, and secure long-term food security for the 21st century by pushing life deep into the white sands of the Sahara Desert. They took the first steps in the New Delta project in 2021 when construction officially began on a 114-kilometer artificial river designed to carry water from the lower reaches of the Nile River across the Arab desert. Because of the project's massive scale, the Egyptian government mobilized more than 12,000 workers, along with hundreds of heavy-duty trucks, excavators, and bulldozers operating continuously across the site. During peak construction phases, long convoys of machinery lined up in the middle of the desert, running almost 24/7 to stay on schedule. The entire construction zone was organized like a mobile mega-work site, with transportation routes, refueling points, and maintenance operations carefully planned and coordinated. This construction took place on constantly shifting sand. Hundreds of bulldozers were deployed to level sand dunes, cut down high ridges, and redistribute sand into lower areas. The goal was to create a flat, stable surface strong enough to support heavy construction machinery without the risk of subsidence. Each section was carefully graded under strict supervision, with survey engineers continuously checking elevations and slopes to ensure uniformity along hundreds of kilometers of open desert. Conveyor systems removed excess sand from the work zone, while compactors gently compressed the surface layer, forming a workable and reliable foundation. After more than 2 months, once the sandy ground had stabilized, hundreds of excavators and trucks are working to shape the surface of the artificial riverbed. The artificial river was shaped with a wide U-shaped cross-section, featuring a channel bottom about 150 feet wide and an average depth of 23 feet, allowing water to flow naturally without the need for pumping systems. Each day, around 70,000 tons of sand and soil were removed from the desert along the construction corridor of the New Delta Artificial River, stretching nearly 250 miles from the lower reaches of the Nile toward the new agricultural plain. More than 1,200 engineers, operators, and workers labored continuously in rotating shifts, enduring daytime temperatures that frequently exceeded 115 degrees Fahrenheit under the harsh desert sun. The entire longitudinal slope of the entire route was controlled with extreme precision, just 1 inch per 100 feet, an almost unimaginable tolerance for a structure extending hundreds of miles. Survey teams constantly checked elevations using laser leveling equipment every 160 feet, ensuring the riverbed remained straight and uniform throughout the entire alignment. Most of the excavated sand was reused to build embankments along both sides, forming levees between 10 and 16 feet high. In elevated areas, bulldozers cut the ground layer by layer, while in lower zones, trucks continuously delivered reinforcement material until the design elevation was reached. In sections with weak soil conditions, engineers drilled 16-inch diameter sand piles down to depths of 20 to 25 feet to harden or stabilize the ground by mixing cement and clay to prevent future subsidence. Under the blazing sun and amid dust-filled desert winds, long convoys of vehicles and machinery moved in continuous formation, operating without a pause. This earthworks phase lasted for many months in Egypt's western desert, where the challenge was not only extreme heat and dryness, but also the desert sand itself, which can rapidly absorb and drain away water. For that reason, the next stage, lining and waterproofing, was considered one of the most critical phases of the entire New Delta project. First, the riverbed and side slopes were moistened, leveled, and covered with a fine sand layer about 2 inches thick to create a stable surface. Next, 4 to 5 inch thick concrete slabs were cast in sections measuring 16 feet by 10 feet, with expansion joints placed between each segment. These joints were sealed with hot bitumen to prevent leakage and to allow the concrete to expand under the large temperature swings of the Egyptian desert. In areas with weak ground conditions, additional HDPE waterproof membrane was installed beneath the concrete, anchored with steel pins and protected by a sand cover to enhance long-term durability. In total, more than 124 kilometers of the artificial river were lined with concrete, forming one of the largest waterproofing systems ever built in Egypt and North Africa. Along the riverbanks, engineers planted vetiver grass and other drought-resistant plants to stabilize the slopes and reduce wind-blown sand entering the channel. From above, the river now appears as a bright silver ribbon cutting through a sea of golden sand. After the main canal bed was fully excavated and its elevation stabilized, the next structure built was an intermediate regulating reservoir to slow down and control the flow. The first reservoir area was formed by excavating raw ground in layers, creating a wide basin and gentle side slopes to ensure large storage capacity and ground stability in sandy desert conditions. On average, each reservoir covers about 2 hectares, roughly equivalent to nearly 3 standard football fields, large enough to absorb and smooth out flow fluctuations coming from the main canal. The entire reservoir bottom was compacted, then lined with an HDPE or bitumen waterproof layer to prevent seepage and ground settlement. On top of this lining, large concrete panels were either installed or cast in place, forming a durable, load-bearing surface resistant to long-term erosion. All panel joints were carefully sealed to ensure the reservoir can operate reliably for decades. Next, the inlet and outlet control structures were constructed, allowing precise regulation of water levels and distribution of flow into downstream canals or pipelines. Finally, the surrounding embankment slopes were reinforced and finished, turning the regulating reservoir into a hydraulic buffer that protects the entire downstream water conveyance system. After the regulating reservoir, the next stage was the construction of the water control weir. Construction began with deep foundation excavation and shaping of the base to the exact design elevation, ensuring sufficient load-bearing capacity in sandy desert soils. Dense reinforcement steel was installed in segmented bays, forming the structural skeleton for the massive concrete body above. Formwork and scaffolding were then fully assembled, allowing precise shaping of large concrete walls, beams, and slabs. Concrete was poured continuously using long-reach pump booms, evenly layered to create a monolithic structure and minimize construction joints. Throughout the pouring process, elevation and surface flatness were closely monitored to ensure that future water flow would not cause localized erosion. Once the concrete reached the required strength, the formwork was removed, revealing the completed concrete control structure. Once the concrete structure of the gated control dam reached its design strength, the next step was the installation of the water regulating connections at each discharge bay. Large diameter steel pipe segments were precisely lifted into position and aligned coaxially with the openings that had been preformed within the concrete structure. The pipe flanges were pressed against embedded steel base plates and then secured using high-strength bolts to ensure long-term stability and watertight performance. During bolt tightening, the engineering team carefully controlled and balanced the clamping force around the entire circumference to avoid misalignment and localized stress. The joints were then inspected for sealing integrity, elevation accuracy, and flow direction before moving on to the next installation stage. Once all connections were completed, the entire pipeline alignment was checked for coaxial accuracy, and the interior was cleaned to remove any residual materials before the system was commissioned. Next, a system of branch lines was built to carry water deeper into individual agricultural zones. Unlike open canals, this system was formed by large parallel steel pipelines, with each line operating as an independent distribution branch.